Alrighty, folks, just allow me a few moments to walk you through what is a very long warm-up. What you're going to see here in your warm-up with regard to number 1 and 2 are just a graph of a function and then a graph of its inverse. So let's take a look at that first one. When I asked my calculator to graph the function f of x equals x squared, I just wanted it to graph x values bigger than 0. So when you go ahead and look at your t-chart, I was only grabbing x values that were 0 or bigger. And that's why you only see y values like 0, 1, 4, 9, and 16. And that particular graph is going to produce half of a parabola because I only wanted values that were greater than or equal to 0. Then, if you recall from our section on inverses, to get these red values here, all I have to do is switch the rows on the t-chart. So what you're going to see is that my x's become my y's, and my y's become my x's. Plotting those, you get half of a sideways parabola. Now what's interesting, if you took some time to finish problem number 2, is that you get the exact same picture, but we're asked to start with a different function. So when you start by letting your calculator graph y equals the square root of x, picking some easy numbers off of that t-chart, you get some decimals there, but the square root of 0 is 0, the square root of 1 is 1, the square root of 2 is irrational, I rounded it to 1.4, the square root of 3 is also irrational, I rounded it to 1.7, and then the square root of 4 gave me 2. When I took a second to plot those points, I got this half sideways parabola. The exact same half sideways parabola I got when I graphed the inverse of x squared. Do you see how the red graphs match up? Next, I took a second to graph the inverse of that t-chart, and remember from our section on inverses, when I need to graph an inverse, I just interchange the two rows. So my x's became my y's, and my y's became my x's, and that produces, oh, look at that, half of a parabola. So what we can infer from this, some pretty cool stuff. The relationship between these two functions is that they're inverses of one another. And that actually makes sense if you think about it. Whenever we had to solve a square root equation, we squared both sides, and when we had to solve an equation that had an x squared in it, we would square root both sides, so they undo each other. And take a second so you can check your domain and your range. This pattern doesn't just exist for x squared and our square root function. It exists for cubing and cube roots too. So now we're taking a second to go over your t-charts for number 6 and number 7. I can make them a little bit bigger for you. Woo. So I did let my calculator do some of the walking there. If you just type in y equals x to the third, and then press graph, and then go to your table. If you cube negative 4, you get negative 64. Cubing negative 3 gives you negative 27. Cubing negative 2 gives you negative 8. Cubing negative 1 gives you negative 1. Cubing 0 gives you 0. Cubing 1 gives you 1. 2 gives you 8. 3 gives you 27. And 4 gives you 64. Now I could only fit a couple of those on my viewing window there, but I plotted what I could and I got that blue graph. Remember, to graph an inverse, you just switch your rows. So again, your x's become your y's, and your y's become your x's. So I got the red graph right in there. And then what's interesting to note, even though we have different numbers on number 7, you still get the exact same picture. And you can pause at any point in time in the video today to kind of just stop and check your values and make sure that they're right. But though we have different numbers, please just notice that we do get the exact same picture. So what does this mean? It means they're inverses of each other. X cubed and the cube root function are inverses of each other. So now what we're doing is we're taking some time, now that we've, done a little bit of graphing with inverses, we're going to go ahead and play around with our parent functions. And to be very clear, the focus of today's lesson is just to graph square root and cube root functions. So all we're doing is taking our parent function for the square root of x and our parent function for the cube root of x and doctoring it up a little bit from this point forward. So with regard to number 11, you would take a moment to enter your function into your calculator. And then I produced the t-chart that you see here. So if I plug 0 into this function, I get 0 times a half, that's 0. If I take the square root of 1, I get 1 times a half, that's a half. The square root of 2 cut in half is 0.7. The square root of 3 cut in half is 0.87. And then the square root of 4, then cut in half, is 1. And I did jot down for you the t-chart for our square root function. Again, the square root of 0 would give us 0. The square root of 1 would give us 1. The square root of 4 gives us 2. And the square root of 9 gives us 3. And then I did take some time to plot those on the graph, because the problem asked me to compare the graph with y equals the square root of x. So I'm trying to just draw a comparison between our parent function and this new one that has the 1/2 in it. What I notice is that the domain and the range of my graph of y equals 1/2 the square root of x is still starts at 0 and heads towards positive infinity. And that's this blue graph right here. So I start at 0 and I head towards positive infinity. And you may have noticed that for this particular picture, when I visually compare the blue graph to the red graph, what I see is I have the same domain and range, but y equals 1/2 x doesn't quite grow as quickly. That factor of 1/2 causes me to level off the growth. And then for number 12, down here, very similar. First focus is just look at your parent function. So we have y equals the cube root of x this time. And for a cube root function, we're allowed to take the cube root of a negative number. So you see I have some negative perfect cubes here. So the cube root of -8 is -2. The cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. And then the cube root of 8 is 2. And then I plotted those. So that's our general parent function and how that looks for today's lesson. And then what I did is I typed this in my calculator, and I got some numbers for my t-chart there, and plotted that in blue. And then I was just asked to compare the graph with the red graph. Well, when I look at this blue graph, it does go on forever and ever in both directions. So I have a domain and range that sort of matches that idea. Our domain goes from negative infinity to positive infinity, and our range goes from negative infinity to positive infinity. So I'm just leaning on my calculator at this point to graph, but by the end of the lesson today, you really won't need that so much. The comparison, what I notice, is that they still have the same domain and range, but y equals -3 times the cube root of x is both reflected, so I see a flip here, and stretched. I see it's kind of flipped over my x-axis, which does happen quite a bit when we have a negative a value. Speaking of a and h and k, they are a big part of today's lesson. So I had you just on the next slide here, taking a few minutes to review those. So we're going on to that next problem. Feel free to pause if you need a minute to fill things in or rewind. Okay. So with regard to number 14, you're going to see two graphs. Again, I started just by graphing the square root of x. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 outputs 2. So I get the 0.4 comma 2. So that's that blue graph right there. Then I went ahead and I typed this in my calculator. Be careful, when you go ahead and type this in your calculator, the new calculators do it automatically, but you got to make sure you quantify your radicand. In other words, those parentheses should be there when you type it in. And you go to your t-chart and you grab a couple of points, and that produces that red graph right there. So what I see is the domain and the range have suddenly moved. The domain starts at 1 and heads towards positive infinity, and then the range starts at 2 and heads towards positive infinity. Very curious, though, look. So my h value, where that normally hangs out, is 1, and the domain switched to 1, and the k value is 2. My range value moved to 2. As far as f of x is concerned, though, the domain and the range there doesn't change. I still can't take the square root of a negative number. So in our parent function, I have to start at 0, and it'll head towards positive infinity. And because you can't square root a negative number, you're not going to get a negative number back out, so the range also starts at 0. Okay, as far as your prior knowledge is concerned, I wanted you to kind of think about a, h, and k a little bit. And what you see in here is our standard form of our equation for today. We have y equals a times x, the square root of x minus h plus k. And in general, what happened to this red graph? Well, it moved to the right 1 unit. It moved up 2 units. So every point moved to the right 1 unit and up 2 units. Right 1 unit for that first point. And then up 2 units. And then it was stretched by a factor of 3. Now taking this, question number 16 there is asking, what would the cube root function look like? Well, it would look very similar. It would just have a 3 in there instead of a 2. Now we get into the gist of today's lesson. So the goal for today's lesson is to graph radical functions. Super easy to do. We break it down into 2 simple steps. The first thing we're always going to do is take a minute to sketch the graph of our parent function. That's either y equals a times the square root of x, or y equals a times the cube root of x. Then we use our h and k values to shift the graph horizontally h units and vertically k units. So here in example 1, the first thing I need to do is identify my parent function. And that's easy to do. I just usually circle these things out in front. So the parent function in this problem is just y equals 2 times the square root of x. And all I do is I make a t-chart for that function. So again, I can't square root a negative number, so I'm going to pick things that are easy to take a square root of, like 1, 0, 1, 4, 9. and then I take these values and I plug them in for x in my parent function. So for instance, the square root of 0 is 0 times 2. 0 times 2, that's just 0. The square root of 1 is 1. 1 times 2 is 2. The square root of 4, that's 2. 2 times 2 is 4. And then the square root of 9 is 3. And 3 times 2 is 6. So I plot these. This is my parent function. So I plotted 0, 0, and then 1, 2, and then 4, 4. 1, 2, 3, 4, up 1, 2, 3, 4. And 9, 6 isn't going to fit on here. So I'm good with that for right now. And then because this isn't my answer, I always draw it in as a dashed graph. Okay, now I'm done with step 1. I sketched my parent function. On to step 2. I need to translate the graph horizontally h units and vertically k units. So what that means is that I need to figure out what my h and my k are. So what I see right there is a +1 in my radicand. That tells me that this graph is going to move to the left 1 unit. And then this k value right here tells me I'm going to move my graph down 1 unit. So I have to now take these points and I'm going to shift them all to the left 1 unit and down 1 unit. To the left 1 unit and down 1 unit. To the left 1 unit and down 1 unit. And here's how that'll look. So if I shift that first point that's at the origin, left 1, down 1, whoops, not really calibrated here, that looks like the point -1, -1, and then left 1, down 1 for this guy, and then left 1, down 1 for this guy. And then I connect those dots. Ta-da! I graphed a square root function. It's always going to look like half of a sideways parabola because parabolas are x squareds and a square root and x squared are inverses. Alright, now on to our domain and our range. So this graph started at -1 and went to positive infinity for my x values. And the first y value I plotted was also at -1. And then that also went to positive infinity. Alright, let's try it again. Next example here. We have, this time around, a cube root function. So what we're going to go ahead and do is, first of all, make a t-chart for our parent function. And that's these guys right there. So I'm going to go ahead and do y equals -2 times the cube root of x. And I always like to pick numbers that are easy to take a cube root of. So for me, I chose numbers like -8 and -1, 0, 1, and 8. So the cube root of -8 is -2, and then multiply that by -2, I get 4. Plugging in -1 gets me an output of 2. Cube root of 0 is 0 times -2 is still 0. Plugging in +1 evaluates to -2. And plugging in +8 evaluates to -4. So I'll go ahead and draw that in. Notice my scale is by 2 this time around. So to plot the point -8, 4, I go over -2, 4, 6, 8. So I'm going to go right there. Whoops. Forgot to move up. Okay, -8 and then up 4. And then -1 up to, that'll be half a tick mark over, 0, 0, over 1, down 2, and then 2, 4, 6, 8, down 4. So I get this graph that's definitely reflected and more stretched out than our normal cube root. So our cube root function always makes this s. It's just an inverted cubic function. It's reflected over the line y equals x, so it's an inverse. Okay, next, to get the answer, let me make this dashed real quick here. Let's make some little eraser marks. Trying to take out too many points. There's my dashed graph. And then I'm going to look at my H and K to try to figure out how to translate this now. So this is step 2. And because that's a -3, I know this graph is going to move to the right 3 units and then down 2 units. So I have to take all these points, I'm going to move them to the right 3 and then down 2. Remember, if you're moving to the right 3, that's a tick mark and a half because we scale by 2. So if I go to the right 3 and down a whole tick mark, I'm right there. To the right 3 and down a whole tick mark is that one. If I take this guy and move it to the right 3 and down 2, I'm right there. And then I got to take this guy, move it to the right 3 and down 2, so that'd be right there. And then this guy won't fit. I'll try to get him to fit. So right 3 down 2 would be right there. Make a little mark off the grid there. And then I would connect those with my nice little sideways S. That's my parent function for my cube root. There it is. That is your answer. Notice we go from negative infinity to positive infinity for the domain and the range. These graphs go on forever and ever. All right, let's apply this business. So, pretty simple word problem here. We'll read it together. The period of a pendulum. Pendulum is like a needle that swings back and forth. Maybe you have one on one of your clocks at home. The period is the time something just takes to cycle back and forth. So the period of a pendulum is the time the pendulum takes to complete one back and forth swing. The period, t in seconds, so this is time, can be modeled by the equation t equals 1.11 times the square root of p, where p is the pendulum's length. Now what's curious to me about that is that this time around our time is actually the y value. It's the one time every once in a while that springs up where time is not our control variable. And so our x values are actually the length of the pendulum in feet. So when I think about time in seconds and length of a pendulum, I'm just trying to restrict my x values in my head to kind of make sense. And I'm only really going to need positive values for length and for time. So my x min, I'd probably just start it at 0. And then, I don't know, what's the biggest a pendulum can be? Maybe 10 feet. And then I'd just scale that by 1s. And then time it takes for one to cycle back and forth. Well, I don't need negative time, but I don't know, 15 seconds maybe? Seems long, but probably use that. And then I maybe just scale that by 1 or 2. And then in your y1, in your calculator that is, you would just type in 1.11 times the square root of x. And then you would just press graph. When I did that, so like this is 0, my y max was 15, and then this went out to 10. I just got just a rough sketch there. I just got something that looked a little bit like that. Then part B, it said use your graph to determine the length of the pendulum after 3 seconds. So they're saying, hey, let your big T be 3. Well, in this case, that means that they want us to basically figure out when is Y 3. So you could just trace. So I would trace on my calculator, and that's what I did do. I just don't have one on my iPad here for you. So I traced until I got a Y value at 3. And you can go ahead and try to do that now if you'd like, and pause for a minute. So if you trace that particular graph, just tracing this guy until you get that Y value of 3. And we're going to try to figure out what the X value is. And when I did that, I did get an x value of about 7.3 feet. And our conclusion is just to verify that that is indeed the case. So based on our algebra work, does this answer to the above problem make sense? Why or why not? So what we're asked to do is just let our t equal 3. We're trying to figure out the length of a pendulum that would take 3 seconds to move back and forth. So in my equation, I would replace the t with a 3 and then solve for p. So that means I'm isolating and then I'm going to need to eliminate that radical by squaring both sides. And then, hey, look at that. I did get about 7.3 feet. So, does the answer make sense? Well, look, they both match. So we could say yes. Makes sense. A couple reasons. Our graph does produce a response that our algebra confirms. And it kind of makes sense you could have a pendulum that's 7.3 feet long. I know I've seen some pretty big ones in my day too. All right, congratulations. This is the last section in Chapter 6, and you've all worked really super hard. Feel free to rewind, or watch something again, or ask me questions in the next lesson.